Thank you very much for the opportunity to speak. It's really nice to be back. And I remember 3 years ago, I was a fresh postdoc here, and in the short members seminar, I claimed that I was going to spend some time thinking about arborealization. So it's great to have the opportunity to come back and report. And I would like to frame it in a more general context, which is that of recent developments in flexibility of caustics. And so I'm going to try and explain the whole story. That there maybe won't be a lot of proofs, but hopefully I can still give an idea of why things are true. So first of all, I would like to just give a bit of a prelude so that we know where we're going, and just mention the theory of ribbon graphs, which is very classical theory. So what's a ribbon graph? So a ribbon graph, it's a finite connected, say, trivalent graph G, and it's equipped with a cyclic orientation, cyclic order of the half edges incident at each vertex. Okay, so if I draw it on the blackboard, then the orientation of the blackboard will specify for me the cyclic order of the half edges. So for instance, I could draw a graph like this, and then it will be understood that the cyclic order of the half edges is given by the plane. And I can thicken this ribbon graph by just along each edge, thickening each edge to a strip, and each vertex thickening it to a disk, and I will get an open Riemann surface. So from a ribbon graph, I get an open Riemann surface, and I can go the other way. It's easy to see that every open Riemann surface can be obtained by the thickening of a graph. You just take a Morse function, take critical points, and you'll have vertices for the minima and edges on the saddles, and the cyclic ordering really matters, right? I could draw the same graph topologically, but change the cyclic ordering on one of the edges, and then if I thicken this, then what do I get? I get a different open Riemann surface. So this is of course just the pair of pants. This is a once punctured one surface. And okay, so you can moreover attach some lengths to these edges and really recover honestly the holomorphic structure, but today we're just going to think about symplectic structure, and indeed that's a part of the story that will generalize. And there's a uniqueness, right? So it is a fact that's not too hard to show that if two ribbon graphs correspond to the same open Riemann surface, only if, but this is the interesting direction, then they are related by a finite sequence of moves following. Well, okay, actually let me make a small correction here. Trivalent, let me allow univalent edges also. So for the zero parametric, you don't need the univalent, but parametric, it's good to have them. So there's two moves. The first one takes a local picture like this and replaces it with this one. This in Morse theory corresponds to a handle slide, or half of a handle slide, really. And the second one corresponds to birth death, and just has, well, it corresponds to the creation of a univalent vertex. Just appears. And then that's it. And these are all the moves, and you can prove it with Morse theory if you want to. And indeed, you can use ribbon graphs to even give a combinatorial description of the moduli space of open Riemann surfaces. And so what the main application that I want to discuss today of this flexibility of caustics will be to a generalization of the theory of ribbon graphs to arbitrary dimensions in the context of Weinstein manifolds.
But when you say Riemann surface, there's not really any complex structures here.
No, well, like I said, in the case of Riemann surfaces, if you attach lengths, and then that corresponds to like just the length then you can actually recover the complex structure, but in higher dimensions, this is just hopeless. So
sure.
Yeah. Okay, any more questions?
It's clear you'll only get orientable things when you do this.
Yes. Well, it's yes. Yes.
Okay, so they actually, it's a one-to-one correspondence.
Yes.
It's not okay.
Yeah, because I have the cyclic orientation. So yeah. Okay. So let's just keep that in mind, but let's switch gears for a little. So what is a caustic? Okay, well, it's useful to keep both points of view at the same time. So let's consider two settings. So I have a symplectic manifold, or I have a contact manifold. Some Lagrangian distribution in M, or some Lagrangian distribution in the contact distribution, which is itself a symplectic vector bundle. Well, maybe conformally, but the notion of Lagrangian is still well defined. And I have some Lagrangians of manifold. Or Legendrians. And the symmetries that we will consider are here Hamiltonian isotopies. Here just the Legendrian isotopies. Okay, and so the main question is, to what extent can I simplify the tangencies of L with respect to gamma via either a Hamiltonian isotopy or Legendrian isotopy? And the main result is that this problem abides by a full H principle. Okay. So before I state the result, let me just, so good examples to keep in mind are when is, say, a cotangent bundle. That's just the vertical distribution, or when N is a cosphere bundle. Again, gamma is tangent to the fibers. And the simplest, or you can consider, if you prefer, the front projection for a one jet space. And the simplest possible tangency that you could hope to have is the fold, and it takes slightly different incarnations in the symplectic world and in the contact world. So in the symplectic world, I would have a parabola up here, and it projects down there. And so locally in coordinates, this is just a map x goes to x squared. But of course, if I take the Legendrian lift, it's going to be something like this, and I project it there, I get a cusp. And so this is in the Legendrian world, the folds are really semi-cubical cusps. So this is the simplest possible caustic that you could hope to have, and unfortunately, generically, the singularities are much more complicated than folds, and in some well-defined sense, unclassifiable. So just you cannot solve the problem of simplifying these tangencies just by generic perturbation. You have to take some very carefully chosen perturbation that is produced to you by the H principle. And so let me just phrase the main result. I'll just phrase it in the symplectic category for simplicity. So the main result, which was what I spent my thesis doing, is the following. So L is Hamiltonian isotopic with L prime, such that the tangencies, let me denote by sigma L prime with gamma, are only folds. The problem of simplifying the tangencies to be only folds via Hamiltonian isotopy is equivalent to the formal problem, namely whether gamma is homotopic through Lagrangian distributions to gamma prime, such that the tangencies of L with gamma prime are only folds. And just some remarks in this form because it's just easier, but this is a full H principle, so C0 close, metric, relative, etc. You can soup it up for other types of co-rank 1 singularities. Any homotopically allowable co-rank 1 locus can be realized if and only if it can be realized formally. Some results in this direction were first proved by Entov using a surgery technique, which was symplectic and contact generalization of Yasha's surgery for smooth maps. And just very briefly, let me describe what are the two main ingredients in the proof. So the first one is a holonomic approximation type result with controlled cutoff. So this is a little bit in the spirit of what Bernard was talking about, that you need to be careful with cutoffs when you extend local solution. So holonomic approximation gives you a local solution near a positive codimensional subset, and then if you extend willy-nilly, you might have some problems. So it's some holonomic approximation with controlled cutoff. But somehow you don't just want to control the R-1 jet, you want to control everything except for pure order R partial derivative. So I call that per holonomic sections. And it's related to Gromov's idea of iterated convex hull extensions and convex integration for higher order jets. And the second one is a wrinkling process for Lagrangians and Legendrians. And again here, so if you want to wrinkle, how do you do it? How do you generate? What's the generating function for a wrinkle? Well, it's just like a Riemann-Meister 1. So it's kind of pretty clear how to create wrinkles. You just insert this model, but then again, there's a slight issue of cutting the wrinkle off. And here you need to be a little bit careful with exactly the shape of the cutoffs in each direction. So again, there's a little bit of some care, but it works. And just a word of caution that these wrinkles have nothing to do with Emmy's wrinkles. Like Emmy's wrinkles happen in the front projection, but the wrinkles here happen in the ambient contact or symplectic manifold itself. So it's kind of wrinkling in a different place. In particular, these are perfectly smooth embedded Lagrangian or Legendrian submanifolds.
The wrinkle or the singularity appears when you project into half the coordinates, or
That's right. So the singularity here appears when you say your Legendre is here, then it's a singularity of this map.
I thought you were trying to find the ratio. This for the same one.
Well, it's
both.
yeah. So for instance, in this case, you would have maybe say a cotangent bundle, and then you have some Lagrangian. And the tangencies of the Lagrangian with respect to the vertical distribution are the same. So this is cotangent bundle. Here's the zero section. So then the tangencies are the same as the projections of this map to the base. So I think that's all I want to say about the theorem. So any further questions? Okay. So, people in flexibility are very happy when they reduce a problem to algebraic topology, but it turns out algebraic topology is not entirely trivial. So in fact, kind of checking when this condition holds is not yet fully understood. So one thing that I assigned to an undergrad this past year, and because there were just a couple of things to check for spheres, is to clarify this homotopical condition when L is, say, a homotopy sphere. So when L is a homotopy sphere, I can think of the homotopy class of the distribution gamma in the space of Lagrangian distributions as just an element of pi n of the Lagrangian Grassmannian un mod on. And then the problem of simplifying the singularities is equivalent to just asking that this element is stably trivial. Here we're in the metastable range. Well, once we stabilize once, we're already in the stable range. So take U1O or UN plus 1 mod ON plus 1. So in the case of spheres, it's fully understood. And the natural conjecture is that the condition that the Lagrangian distribution is stably trivial is in fact necessary and sufficient. It's definitely necessary. So that would be a natural claim. And I mean, after we prove this, kind of Yasha came up with a better argument, and I think it's possible that that argument can be used in an inductive way to possibly prove an analogous statement in general, but we don't. I don't think that for the moment.
Can you efficiently check the last condition? So when elements are in this kernel, I mean, okay, so the target has something to do with K-theoretic stuff, I guess, but
in general, if you don't have any information, you don't know. Okay. But as we will see in certain situations, with some assumptions you can do. But in general, the distribution could not be stably trivial, and then there's a different problem, which is what are these groups are known. And so in principle, you could just understand explicit representatives for all of them, and then use a stronger version of this theorem, which is true, and then you would have a list of all the homotopically essential caustics of spheres. But I also have not fully understood that yet, so I'm not sure what is that list. So next, I will explain an H principle for the elimination of caustics without preconditions. Okay, and you can ask, well, what is an H principle without preconditions? If we accept the philosophy that everything is an H principle, then it's just a theorem. So let's just write a theorem. So for that, I need to introduce a class of singularities called Ricci. So the Ricci, well, a ridge of order 1, very simple object, is the following thing, is the union of two half-lines in space. So it's just that guy. Okay. And in general, ridge of order k.
Thanks.
Yeah, we'll just, yeah, is r to the k. R to the k. Just k. And like F says, or more generally, I will call any stabilization an order k ridge. Also an order k ridge. So for instance, an order 1 ridge would also be ridge times the factor, and for higher order ridges, well, you should imagine somehow 4. Let's see. 4 Lagrangian planes meeting at a point and intersecting in codimension 1. So for example, order 2 ridge, you can think of as in R2 the union of a quadrant, the positive conormal to a half-line, positive conormal to this other half-line, and then a quarter conormal to a point. So in blue are 2 different Lagrangian planes, and yellow is another Lagrangian plane, and in orange is the 4th Lagrangian plane. Okay, so that's a ridge, and a ridgy isotopy. A Lagrangian submanifold, a symplectic manifold, consists of the following thing. So the first thing that you do if you want to deform a Lagrangian by a ridgy isotopy is that you introduce ridges. Introduction of ridges. Along a union of hypersurfaces. Okay. And these hypersurfaces are assumed to be mutually transverse in the strongest possible sense, and bounding. But let me not write that. And after you've done that, you may deform the result by Hamiltonian isotopy. So start with some smooth manifold. You have a union of hypersurfaces. You introduce ridges along these hypersurfaces. And then you further deform the result by whatever Hamiltonian isotopy. And then you have something that is a singular Lagrangian submanifold, but the singularities are modeled on these.
Bridges, you're sort of just making it a non-smooth thing, but you have a good model.
That's right. You explicitly use this local model in the neighborhood to just introduce a ridge. Okay.
Is the ridge then approximated by smoothing or not?
You can always smooth it out.
Keeping it Lagrangian.
Yes. You can always smooth it out, keeping it Lagrangian. Because you can always smooth out the local model by keeping it Lagrangian, because everything one-dimensional is Lagrangian, then you just take products.
In your definition of isotopy,
What's that?
are you allowed to also remove ridges?
No.
So it's not symmetrical.
You're only allowed to create ridges. Does anyone have long arms? Another eraser.
Between two.
I guess we need headphones.
Yeah, sorry about that.
So you are also read.
As defined, it's not.
Oh, I always wondered what's the use of that. Oh my God, it's. What to think of it rather like correspondence then.
Got it?
Amazing. Okay, so yeah, so you're only allowed to create ridges. You're not allowed to destroy them.
But if you think kind of like in going in reversing time.
In reversing time, you can yeah. Okay, so then the theorem. And by the way, everything that I'm going to explain from now on is joint work with Yasha and David Nadler. And it came out of a collaboration that we started with Laura Starks. I'm just not going to write. I'm just going to write things that are true. Okay, so then what is the theorem? The theorem is that without any, so for any Lagrangian distribution, there exists LT, actually C0 small, Ricci isotropy. Such that L1 is transverse to gamma in the sense that at singular points, every plane, Lagrangian plane tangent to the Ricci Lagrangian is transverse to gamma. So what you do is you completely eliminate the tangencies at the cost of introducing some genuine singularities of the Lagrangian. But these singularities are very simple. Now you might say, well, why don't we just smooth it? And then, you have some statement about in the smooth category. And the problem is that the moduli of Lagrangian planes that are transverse to a Ricci object has moduli, or at least it appears to have moduli. And so it's not, you don't get somehow as clean a statement in the smooth category. But as we will see, this is sufficient for the applications that I will describe. Okay, so that concludes the discussion of the rigification theorem. This is called the rigification theorem. Okay, any questions?
What's the?
It's a half dimension.
Half dimension.
Lagrangian distribution.
Yeah.
Okay.
More questions?
But kind of like, of course, it's not part of the thing, but the whole story certainly has a purely smooth analog.
Yeah.
There's an arbitrary codimension.
Of course, but we didn't write that, so. Yeah. Yeah, so indeed, if you just had smooth objects and you could introduce analogous smooth notions of ridges, but I mean we just don't have any particular reason to do that, so we didn't do it, but it certainly can be done. Okay. All right. So let me keep this here. I will return to it in a second. So now I return to the original motivation, which is generalizing the theory of ribbon graphs to arbitrary dimensions. Okay, and so the objects that we consider are Weinstein manifolds. Let me just talk about Weinstein domain for simplicity. So, the risk of boring the experts, let me just remind you that lambda is a one form such that this is symplectic. If I take Z, the omega dual, so the vector field of lambda, then the derivative of the symplectic form is the symplectic form itself. So it's symplectically conformally expanding and is outwards pointing. Along the boundary. So you think of it as some symplectic manifold that has this convex end. And indeed, this is a contact manifold if I restrict the Liouville form to the boundary. Okay, so an example of such is any affine algebraic smooth variety, also known as Stein manifold.
Not necessarily algebraic.
Holomorphic. What I said wasn't false, but yeah, any Stein manifold indeed. Okay, so this is our object of interest, and so you should think of this as a symplectic object underlying, Stein manifold, and then
But you didn't mention phi yet.
oh, thank you, and then phi is so without phi this is just a Liouville manifold, and while these are also objects of interest, much less is known about them, but a lot more is known if we assume that there exists a Lyapunov function, let's say Morse or generalized Morse or Morse spot. There exists some taming of the dynamics. Taming of the dynamics by a Lyapunov function. Okay, so in particular, in the presence of such a taming function, W has the homotopy type of a half-dimensional CW complex.
So, sorry, little z is different from big Z, or what's?
No.
Is it dual field?
Z is a vector field? Yes. So this just says that Z is gradient like for phi.
Okay.
Yeah. So Z is gradient like for phi. So because of this condition, you will find that the stable manifolds of all the critical points are in fact isotropic for the symplectic form, and therefore their index can be at most half of 2n, which is n. So yeah, so this has a homotopy type. N-dimensional CW complex. And a representative can be taken by the union of the stable manifolds in any Morse theoretic context. So the skeleton is defined to be the attractor of the negative flow, which is of course just the union of the stable manifolds.
Excuse me.
Yeah.
I'm a bit confused about your statement. Isotopy.
Yeah.
So I mean, if I have a Lagrangian,
Yeah.
then the two obvious distribution that you have, one is tangential and one is transversal. I mean, the fiber one in T star and this. And this tangential one you can just change by D of F. So where is this? Why you need this Regis? Can you tell me?
Sorry, what is the question?
I mean, this gamma,
Yeah.
which is two obvious distribution that you take. One is completely tangential to. You're making it transversal, correct? Your L1.
Make it transversal. You have a tangent and you have a vertical distribution.
But it is anyway transversal.
So for instance, suppose
You
that
have an arbitrary Lagrangian in cotangent buffer. And you want to make Lagrangian.
But I can take the Lagrangian and take its tubular neighborhood and then look at distribution here, correct?
yeah, you can do that.
But then what? So
So it's purely local statement in a Weinstein neighborhood of Lagrangian. Yes.
So one can make always Lagrangian transverse to something which is tangential by taking df.
Yeah.
And to the obvious two Lagrangians, it is kind of already transverse. So where is the difficulty? I'm not
But that vertical distribution might not be homotopic to your specified distribution. Like for instance, in this case, I mean, I have a distribution that is transverse to L, but if my gamma has some homotopically essential tangency like this, then I cannot apply the H principle because gamma is not homotopic to, well, I mean, in this case it has folds, but say it had some.
I want one example where the ridge is necessary. Can you draw, like, give me a picture? Of...
It's hard to draw because you need dimension of the Lagrangian at least 3.
You want an example of what?
Why a ridge is necessary?
So in this case, you agree that some kind of singularity is necessary. And in this example, some kind of singularity is necessary. So yeah, in this case, because the dimension is so small, you could smooth it out and then the tangency, it's not so bad. It's just some fold type tangency. But if instead of this, I gave you a local model, say the Lagrangian was 3-dimensional and I give you the local model for say a co-rank 2 singularity. Then this co-rank 2 singularity is homotopically essential relative to the boundary. And so you just won't be able to deform the Lagrangian so that it only has folds. And so the best thing that you can do, or at least one thing that you can do, is say, well, I'm going to get rid of this co-rank 2 singularity at the expense of introducing an order 2 ridge. So when you have homotopically essential higher co-rank singularities, ridges are unavoidable.
Okay.
So we have the skeleton. In this case, it has some critical points. And the skeleton is the union of the stable manifolds. And so one would like to think, or one has the desire maybe to an analogy. So let's just do an example. Right, so W is a cotangent bundle, which is a perfectly nice Weinstein manifold with the Morse-Bott-Lyapunov function p squared, then the skeleton is just the 0 section. And so one would like to more generally think of W as the cotangent bundle of its skeleton, as a thickening, as a symplectic thickening of its skeleton. And in that way, study Weinstein manifolds through the smooth topology of their skeleton. Okay? But this is just not possible in general. And so the simplest example you can think is suppose that I have a Weinstein manifold that has 2 critical points. One is a minimum, and the other one, let's say, has the maximal index. And then what I have is a disk attached to a Darboux ball along the Legendrian. And the skeleton is going to be disk D union the luteal cone on the attaching Legendrian. So it's topologically a sphere, as it should be. And you see so this, it has a smooth structure in the sense that it's a ring space by restricting ambient smooth functions on it. And in this sense, the smooth topology only depends on the smooth isotopy class of lambda, while the symplectic topology of the Weinstein domains depends on the Legendrian isotopy class. So somehow this singularity is too complicated and too much is hidden in the way in this cone. And so just the smooth topology of the skeleton by itself is not enough to capture the symplectic topology of the Weinstein manifold. Is that clear? That's kind of an important point. And so what one can try to do is one can try to blow up. Imagine a half blow up, real blow up of this point. So in other words, let us expand that minimum to a Morse-Bott disk. So that now, instead of the Darboux ball, the symplectic structure that I have is just, well, cotangent bundle, probably you want unit disk, so it's compact, but cotangent bundle of an n disk. It's different n disk. Let's say this is the stable disk here. Okay, and in that case, well, you have the same picture. You have a Legendrian on the cosphere bundle again, and you're attaching a handle there. And the skeleton is given by the same formula. It's that attaching disk. Well, okay, the skeleton in this case is a little bit more. So skeleton in this case is the attaching disk, union the cone on lambda, but also union just the base disk. Okay, but this cone now is a cone on the cotangent Liouville structure instead of the radial Liouville structure of the ball. And therefore, what are the singularities of the skeleton? They're the caustics of the projection of the Legendrian onto the disk. So I get some kind of front there, and the skeleton is now like that. So if those caustics are very simple, then the singularity of the skeleton is very simple. But if these caustics are very complicated, then the skeleton is very complicated. Okay, and thus the problem of simplifying the singularities of the skeleton is intimately related with the problem of simplifying caustics. So Nadler described a simple class of singularities that he was hopeful would be sufficient to represent any Weinstein domain up to homotopy. And it's the class of arboreal singularities. So these are, let me give a quick geometric definition. So these are classes of germs of isotropic subspaces of symplectic or contact manifolds, and they're defined by the following axioms. A point inside the cotangent bundle of a point is arboreal. If I have something that is arboreal, then any stabilization, so let's say this is an M, then any stabilization is arboreal. In particular, all smooth Lagrangians are arboreal. Third, to relate the symplectic and the contact category, something is arboreal, let's say an M, if and only if the Legendrian lift, the contactization is arboreal. These are all locally simply connected germs, so I can always take the Legendrian lift. Okay, and then the most important axiom says that they're closed under transverse Liouville cones. If I have a bunch of germs in, let's say, the cosphere bundle of Rn. So these are -1. Oh, and they're centered on points that project down to the same point in Rn. And the projection is transverse and self-transverse in the strongest possible sense. So you take any smooth strata and they're self-transverse. And the union of the zero section with the Liouville cones So let me just draw some examples. So something smooth is arboreal. Now suppose that I have a smooth Legendrian, is arboreal, and it projects transversely down below, then the union of the zero section with a Liouville cone, which is just the conormal to a hypersurface, to a smooth hypersurface, then this is arboreal. But of course I could have maybe two different ones, and they both project down to hypersurfaces that are transverse. And so again, by this axiom, the union of the conormals to these two smoothly intersecting hypersurfaces is again arboreal. And finally, since this guy is arboreal, I could apply this axiom twice. And then I have an arboreal Legendrian up here. And then it says that if this projects transversely, which means that the front will look like this, then the union of the Liouville cone with the zero section is arboreal. So these are all examples of arboreal singularities, and in fact, these are all the arboreal singularities for Lagrangian dimension 2. Okay, and you can conveniently, well, actually, I lie. There's actually two different things that could happen. Here you could have there's two different versions of this, one positive and one negative, because this quadratic hypersurface could either come on the positive or on the negative side of your given plane. And so there's a convenient way to associate some combinatorial data to these objects, and it's a finite rooted tree. I will explain a little bit, but I think you can just imagine how this is doing. This is saying that there's a zero section and there's a single piece coming in. This is saying that there's a zero section and there's two independent pieces coming in. And here we've applied this axiom twice. So you've taken one cone and then another cone. These are classified by these trees. This is why they're called arboreal. They're classified by trees. But then there's this positivity question. And so we will decorate it either with a plus or with a minus. And that's how it goes. So in general, to an arboreal singularity is associated a finite rooted tree equipped with a decoration by plus minus 1 on the edges not adjacent to the root.
All of these singularities are non-compact.
These are germs. So these are germs of singularities. It's just a local. Okay.
They're kind of like not completely trivial, actually non-trivial statement, but this whole singularity. Are you going to put?
I hope I will explain all non-trivial statements. Leave those there.
I have the bottom board up.
Yeah, I'm aware. So,
But the suggestion to slide the lower board up.
yeah, I'm aware of the suggestion, but I'm deciding to ignore it. So the main theorems you will understand why. So the main theorems here are the following. So up to simplexomorphism term in this class is uniquely characterized by the tree, by the finite rooted tree. Plus minus decorations. Okay, so first statement, which in our opinion is non-trivial, is that the symplectic topology is just characterized by the combinatorial data. Second theorem, that if skeleton is arboreal, in the sense that all the singularities are in that class, then W is uniquely determined the Weinstein homotopy. And then so this tells you that, that these objects are combinatorial. Arboreal, not quite true. By scale W plus what we call an orientation structure. Which is also combinatorial data, and which you should think is the analog of the cyclic ordering of the half edges at each vertex. So even in dimension 1, this theorem is false. If I hadn't added this, because like you saw for the theta graph, you can have both the parent pants and the once punctured genus 1 surface, but so you need the orientation structure. Okay. And then the main existence theorem is an H principle for arborealization in the positive category. So positive arboreal singularities are the ones where you only get plus signs. And so the theorem is that a Weinstein manifold is homotopic to one with positive arboreal skeleton. Well, it's not hard to see that if you have an arboreal skeleton, you almost have a Lagrangian distribution, because well, you have one on each smooth piece, and then you just need to decide whether you're rotating one way or another. And okay, so there can be an ambiguity, but if they're all positive, then there is no ambiguity. And so this actually implies existence of a Lagrangian, a global Lagrangian distribution. But the H principle says that this necessary condition is also sufficient. And it's kind of peculiar. Because,
sorry, what is the condition?
That there exists a Lagrangian distribution.
Tangent bundle is isomorphic to simplification.
That the classifying map lifts to deal. So, yeah, and so it's kind of peculiar because you think, well, in this scheme, I was saying, well, for instance, if you just have one handle, then of course you can quickly see that this condition will actually allow you to apply the first H principle that I mentioned, and then only get cusps, and then cusps are very similar to arboreal singularities because you can just do this kind of thing. But actually, the problem is when you have a lot of different handles, there's two main issues. The first one is it's kind of hard to localize the homotopical condition to each handle, even if you have a global condition. But maybe more importantly, there's quite subtle point about the interaction of 3 or more strata, because at the interaction of 3 or more strata, you can control the singularities of this stratum falling on this stratum, but then your hands are kind of tied up when you then project to the third stratum. And so what the global field does for you is it gives you a guide for ensuring a compatibility that makes these iterated projections positive in a sense which automatically guarantees that once you've achieved transversality for 2 pieces, then there's transversality with the other pieces too. Okay. Now,
And there's some, you are going to say that there's a general abstraction.
yes. So then in general, if you have some, if in general you want to study whether this is homotopic to one with arboreal skeleton, then like I said, you almost have a global distribution, but there's this ambiguity. However, this ambiguity can be thought of as the Lagrangian field degenerating into an n-1 dimensional isotropic distribution. And we call that an n-1 structure. And again, I won't define it precisely, but just in words, this is a Lagrangian distribution that is allowed to degenerate to an n-1 dimensional isotropic distribution. And so it's easy to see that this is a necessary condition, and the natural conjecture is that this condition is sufficient, but we don't have a proof for that yet. But it's worth noting that this condition is not much more general than this one. Rationally, they're equivalent, and so it's just not true that every Weinstein manifold can be arborealized. And so that begs the question, what is the best one can do in general? Is there a slightly more general class? Is it just, life is what it is, and in general, you cannot always reduce the list of singularities to a finite list of models? It's not very clear, but in any case, already for Weinstein manifolds that admit Lagrangian distributions, there's quite a lot of examples. For instance, complete intersections, and so there's, which are most of what turns up in, say, mirror symmetry, and already people are starting to use this theorem. For instance, there's a recent paper by Dupé and Bide in which they use the arborealization theorem to estimate the Rupier dimension of the Raphukaya category, which you can think of as the maximum number of cones that you need to take to represent any object given a generating set. And so the calculation is a local, you just compute it for the list of models, and then you use the shiftification of life, the Natrapar and Shendy and company, and then you get the estimate for the whole thing. So, and we hope that there will be more applications. But somehow where the real, or at least in my opinion, where the real interest is if you can prove a one parametric statement. And that's what we're working on at the moment. And so the theorem that we have in progress, I should also mention that the Dor-Starkson proved that in dimension 4, and there's no hypothesis. And indeed, every 4-dimensional manifold has an n-1 structure. So that would be consistent with the general picture. Somehow, yeah. Okay, so then the last thing that I want to explain is a theorem in progress, which is that if I have two polarized Weinstein manifolds, these are Weinstein manifolds equipped with polarizations that have positive arboreal skeleta. With gamma I, the corresponding distribution. It's more that if you have a positive arboreal skeleton, you have a distribution. There's a canonical homotopy class that's associated to the positive arboreal skeleton. So then there exists a homotopy, or rather, skeleton are related by a list positive Riemann-Meister moves. Riemann-Meister moves still needs to be defined, but some analogous list of moves as for Riemann graphs, if and only if are homotopic. At this point, you have some uniqueness theorem up to arboreal moves, and then you might hope to try and define some more refined invariants than just the homological invariants.
No, lo tengo, lo siento.
Anyway, I'm finished. This is what I have in progress, and I'll just finish by giving a non-exhaustive list of moves so that you have an idea of what kind of things we're talking about. So now you see why I didn't want to lift this one. This is a partial list of them. So thank you very much for your attention.
Questions?
So the theorem on the top right. So what exactly is the content if you're just interested in a Weinstein manifold given by attaching a single critical handle to a ball? Is it just, I mean,
In that case, there's no hypothesis. You can just apply the rigidification theorem, and that can always be arborealized.
but does it just follow from the simplification of Caustics of the Legendrian, or is it?
This statement, as it's written, does follow from the simplification of Caustics because, actually that follows. So that follows from, and we wrote it in this paper that I wrote with this highly motivated undergrad, because you see, if you just have a single guy, then you can assume that your distribution is just the kernel of the projection on the cotangent bundle part. And then it's easy to see that the fact that gamma extends, or rather, so here nu is like the reduction. So nu is, let's call nu, so pi is the cosphere bundle projection, say. So then the fact that nu, after adding the Liouville extension, the Liouville direction extends to a global gamma, is precisely the statement that nu is stably trivial as an element of pi n minus 1, u n minus 1, mod o n minus 1. And then you can apply the H principle, simplify the caustics, replace cusps with two singularities, and then you're rosy. But you actually don't need the H principle. You can just apply the rigidification theorem here without any hypothesis, because it's only two strata. So there's no subtlety about three or more strata. So in this case, you can just you don't need any hypothesis. You can just apply rigidification. But yes, as it's written, this does follow from the H principle.
So in this setting, you don't encounter this signs of.
No, because the signs, recall that you only have signs for the edges not adjacent to the root. But in this case, the only singularities that you would encounter are singularities of depth at most 1, because you're only taking one cone. So the distance from the root corresponds to the number of iterated Liouville cones that you've taken. And in this context, you're only taking one Liouville cone. So then there's no signs.
See. Can I also ask in general, so what does having only positive singularities buy you? Or why is that something you might want?
I don't think that there's anything immediately clear. It's just a clean if and only if statement. But like if you have a skeleton that doesn't have only positive orbital singularities, then you might not have a global Lagrangian distribution. So it's just not. But I don't know that. I don't know if you have anything to say, Yasha. But
does it somehow simplify the microlocal sheaf theory or the?
No, because I don't think that the categories of microlocal sheaves depend on the signs actually. So it's not clear what it buys you. Yeah. I mean, what it buys you is that we could prove the theorem. But like we just,
correct.
yeah, we could prove the correct theorem. So when I gave the 15-minute talk here 3 years ago, I was saying we're going to prove that all Weinstein manifolds can be arborealized. And it's just not true. So this at least is true.
But positivity is very important in low-dimensional topologies. Is it the same thing emerging here? I mean, in Lefschetz vibrations, it's very important if the Dane twists are all right-handed, and examples that come from a holomorphic world with this property, probably symplectic too. And usually if things have both left-handed and right-handed twisting, some expert like Bob Gompf or someone Ekblue can tear the thing apart and show that it has a simplified hand decomposition. There's just a lot of experience where positivity is. I don't know if it's related.
I'm not sure.
It could be related.
Well, if there's no more questions, thank you again.
Maybe can I ask one question? I mean, we can clap also, but may I ask?
Yeah, you can.
Yeah, thanks. So yeah, thanks for the talk, Danny. So I wanted to ask, you mentioned before, and Yasha mentioned that you could carry out this kind of arboreal smooth theory. And I think we talked about it a while ago, but I don't remember what you said. And my question is kind of like, I mean, you like parametric Morse theory, and one could imagine that a parametric a smooth arboreal program, maybe you could use it maybe to compute the stuff in parametric Morse theory. Is that something you would think about maybe, or does it make sense?
I don't know. I mean, like, to compute things, you will need explicit constructions. Like, for instance, for arboreal skeleta, Roger has some explicit constructions, right, for certain Weinstein manifolds. This H principle kind of stuff is not going to give you any explicit arborealization that might be used for computation. So, at best, you can hope that it lays a foundation for a theory that then, by explicit constructions, can be computed. But even then, in the smooth category, I'm not sure what you might hope to compute.
Yeah, but you can imagine that you can, like, in smooth category, to compute some kind of torsion type invariance using.
Yeah, this is what they.
I mean, you can already compute that with good old-fashioned Morse theories. I mean, what more do you want to compute? Maybe, I'm not sure.
No, thanks.